to look to you right away to kind of set this up for us. What are we talking about with the critical elements, the rare earth, the critical minerals and the rare earth element studies that have been going on, and really, where are we going with all of this?
Thanks, Kay. Good job filling in. Hopefully we can see my presentation.
Yes, I have it live here and we're good to go.
Okay, so this is the Bear Den member of the Golden Valley Formation. We'll be looking at several more outcrops of this as the talk goes along. We've got we put out eight publications so far. I'll be talking about really the last two, the two from this year. But we started back in 2015. You can see these are our study sites, the black dots, primarily focused along the Little Missouri River. That's because the outcrops are really good. Coals are exposed really well, which was our main focus. So we had 300 measured sections. We collected 2,200 rock samples and had 1,700 of those analyzed. So we started collecting samples in the fall of 2015, but we began the project back in 2014. We needed to write a proposal to get it into the governor's budget. And so we were, one of the first state or federal government agencies to begin looking at critical minerals in the country. But I do want to point out that we sat down in 2014 with Dennis James, who at that time was with North American Coal, because Dennis had been collecting samples and having analysis at least through 2014 and maybe even before that. So the private sector had gotten a bit of a jump on us. So we focused on the coal-bearing rocks exposed in western North Dakota. Stratigraphic column here shows those. I've got them outlined in red. About 1,800 feet maximum of rocks exposed that contain coal. We did skip the Cannonball Formation, which is marine and does contain organics, but no lignites. And then we extended that a little bit down into the Hell Creek Formation. So we focused on lignites. Almost 70% of our samples have been lignites that we have had analyzed. Another 20% are organic rich mudstones. A little bit too much ash to be considered a lignite. Then we looked at a number of other lithologies from nodules, barite, manganese, iron nodules, volcanic ash. We looked at several of those. Tungsteins, which are thin kaolinite-rich beds within coals that are essentially altered volcanic ashes. Swelling clays or bentonites, and then the natural coal ashes at the base of clinkers in western North Dakota. So throughout our study, we've been hanging right around 19% of our samples have been above the 300 parts per million, which the U.S. Department of Energy put out as the economic threshold. And when we began in the literature, 169 parts per million rare earths, North Dakota lignites was the highest concentration we could find. That's been pushed up now to close to 2,800. It's a little bit apples to oranges because that sample, the 169 parts per million, probably came from a large either truck size or bucket size sample. We've been sampling in 3-inch intervals. So we're going to focus on two horizons that, as I mentioned in the last two publications, the Bear Den member and then 1,000 feet below it, the rain bed. Both are kaolinite-rich horizons. And we'll just talk about how the Bear Den formed and the Paleocene rain bed formed essentially the same way. But 56 million years ago, coming to the end of the Paleocene, what was been termed the Paleocene-Eocene thermal maximum. There was a time where Earth temperatures rose very quickly, became wetter, And so we had a lot of leaching going on, and soil weathering formed the bleaching zone. These rocks tend to be white, if you noticed when I just pointed them out. And over a period of about 200,000 years, the smectite or swelling clay stones, which are primarily the dominant clays in these rocks, were transformed over to kaolinites, and then the rare earth elements were pushed down, and in some cases then landed in the underlying lignite. And so between the Golden Valley Formation, which the Bearden member is the lower member, and the rain bed, which is the top of the slope formation, they occur in two different areas. The outcrops aren't found together. The Golden Valley, or the Bearden of the Golden Valley, is primarily Dunn County down into Stark County and western Mercer, whereas the rain bed is found from southern Golden Valley County, Billings County, into Slope, Bowman, Adams, Grant, Morton, and then up into Oliver County. So here's a look at, again, at the Bearden member. Instead of being bleached white through here, because there's a lot of iron in the system, you get a lot of reds and oranges. And this is why this is referred to as the orange zone. And what we found is from about the middle of the orange zone, where I've got this white line down into the Sentinel Butte. Here's the top of the Sentinel Butte right here. Probably it's a little variable depending on these lithologies, but 10, 15 feet maybe into the Sentinel Butte is where we tend to find enriched lignites enriched in rare earths. And so here you can see there's two thin lignites running through here at the base of the Bearden member. This is called the gray zone informally, but we've got rare earth concentrations ranging from 1,500 to 1,900, and significantly enriched. Normally lignite in North Dakota in our samples have been running about 220 parts per million. Another outcrop of the Bearden member of the Golden Valley. This is in Dunn County. Again, the top of the Bearden. Here's that orange zone where you can see now it's white in many areas, but it has a orange layer running through it of primarily limonite, iron oxide. And here again is that area we bracketed from the middle of the orange zone down into the upper Sentinel Butte, where we've got, these are very thin organic horizons lignites ranging from 800 to 1,200 parts per million rare earth. And then down into the Sentinel Butte, 14-inch coal at the top, close to 900 parts per million rare earths, and then 800 parts per million at the bottom. And this is, we report all of our analysis as dry coal or whole coal versus as an ash basis. We put together this composite column, then plotted the rare earth concentrations to get that, and you can see that within, here's that orange zone OZ, here's the Bearden, but you can see that those concentrations really spike from the middle of the orange zone down into the gray zone here, and then continue high, starting to drop back down to the background in the upper Sentinel Butte formation. And we compare that to earlier work by Klachenko and others, 2007, where they compared the relative percentage of smectite or swelling clays to kaolinite. You can see the kaolinite has a real increase starting again about that midpoint of that bleach zone, or the orange, what's called the orange zone, down into the towards the base of the Bearden member. And again, it coincides with in the lower part of that where we're starting to pick up enriched rare earth elements. We look at gallium, germanium, titanium, vanadium. They don't have the nice pattern that we see with the rare earth elements, and they are they do increase through that zone, but they're also, you see in the upper, the Campbell's Butte member, the upper member above the bear den, towards the base of that, we see increases running through there too. This is the rain bed, so now we're 1,000 feet lower from the bear den in western North Dakota, and we're 5 million years older. These rocks are now 61 million years old. The rain bed is difficult to trace through much of southwestern North Dakota. It seems to come and go as far as the kaolinite content and the bright color of the bed. But this is an area where it's actually fairly easy to correlate. And in fact, one of our sites was taken right from the area that I highlighted. Here at the base of this bleached or weathering zone, we've got a 17-inch lignite, and you see where we sampled through that bed, concentrations as high as 1,800 parts per million, still high 653 at the base. So average is 1,150 parts per million throughout that bed. And throughout this project, we've been looking for a 5-foot thick lignite, and the thinner lignites are much more common, but we've been looking for a 5-foot thick bed that contains rare earth concentrations of 300 parts per million. But this little 17-inch bed contains actually a little bit more than that 5-foot bed. And so when you start getting into questioning, would you set up a small mine that an area where you would mine and then truck this or to a existing coal mine where they would be processing, you'd be better off with a smaller volume to start with than that 5-foot bed that we were chasing. This is from an article in our newsletter that just came out today that Levi Foxness has an article in there on rare earths, and he put this figure together comparing the bear den to the rain bed. The bear den of the orange dots, which you've seen, I showed that before, and here's the rain bed now in blue. Again, you can see here are those weathered, the paleosol or the weathered horizons, and here's the orange zone in the bear den about the midpoint of the bleach zone in the rain bed, so comparable, and then down into below those. And I think you can see again the rare earth element concentrations for these two different horizons match really well. So that's what we were trying to do, is establish an exploration model so companies would know what to go after. We started with 1,800 feet. We found, as you'll see here, that we found high concentrations or concentrations above 300 parts per million throughout that coal-bearing interval, both in the maximum shown in black and the average in gray. But at the two horizons that stand out again are the bear den member up here and the rain bed down here, both when you look at average rare earth element concentrations as well as maximums. So just wrap this up with just to point out germanium and gallium. When you plot that against total rare earth element concentrations, both trend upwards with increasing rare earth concentrations. One thing that we left off here, germanium, our top 5 samples, you may remember from our Hell Creek report, all came from wood, and those germanium concentrations range from 400 up to 700 parts per million. So very high. It'd be great if we could find a thick coal that was very woody that contained those types of concentrations of germanium. And these are graphs that Levi just put together about an hour ago. But then looking at germanium versus ash content, it decreases. And again, that's probably because the highest concentration we were finding, again, with that high wood concentration, which would be low ash. Whereas in gallium, I'm sorry, it increases likely because we're picking up more gallium in the clay content. So that completes my presentation.
Thanks, Ed. I appreciate you going first and kind of kicking us off. And thanks everybody for joining us. We're going to transition now and turn the time over to Steve. He's got some additional work that he's been doing that complements and follows up on some of that initial assessment and technical work that Ed referenced. And would like to thank you, Steve, for joining us and sharing your knowledge about the critical mineral industry in North Dakota. So we'll turn the time over to you. If you need control of the screen, go ahead and take her away.
Well, thanks, Jason. Can you hear me okay?
Yes, we can.
Okay. So what I'm going to talk about today is some of the work that we're doing associated with tools for rare earth element and critical mineral detection, measurement, and sorting. The team that works on this is Alex Benson, Matt Fuca, Eric Kolb, and Eli Pesky from Microbeam. And we're doing a range of different types of projects, and this is a key area that we're working on. So a little bit of background. It's been great. We've been working on everything in coal that doesn't burn, all the impurities, and trying to understand their behavior with respect to everything from fireside performance to emissions to trace elements. And it's great to find that a lot of that work we've noticed critical minerals and rare earth elements in samples for many years, and noted them and just kind of tracked them, everything from coal to deposits to ash and that sort of thing. But we do work in resource assessment, X-ray technologies over here, but also we have a project that is also funded by the through the North Dakota Industrial Commission and the Lignite Energy Council, is the recovery of germanium and gallium from mixed rare earth element concentrates. So we actually have a process for those going from the mixed rare earth element concentrate all the way to the metals. So I just said I'd bring that up a little bit. I know my focus is on the other, but we've been working with everybody along the whole supply chain, from UND producing the materials to the people that process it and turn it into metals, as well as the people that utilize it. So this is pure germanium in a crystal. It's produced by Zone Refining, and it's used in defense applications as well as integrated circuits. So gallium is used in a lot of advanced applications associated with electronic devices. So, but we're working a wide range of these systems to try to come up with technologies to measure, technologies to extract, technologies to refine and purify to get it to six ends of plus purity. So measurement of the critical minerals and rare earth strata can be done with respect to assisting in selective mining and sorting. It's pretty much an essential requirement because of the high variability. If you look over at the plot on the right, the University of North Dakota has went through the process of looking at the development of a mixed rare earth element concentrate plant. But if you look at the tons of material required for a 1 ton per day mixed rare earth element concentrate plant, here's the range of trace elements, not trace elements, but the total rare earth element content, that as you get to lower and lower concentrate, obviously your feed rate goes up. So that's why this critical value here, about 300 parts per million, is a critical one with respect to recovery. Also, if you look at the value, some of the valuable elements like germanium and gallium, being able to bump it from some of the average levels that we see in the amount that we did testing at UND with respect to the some of the bench scale work, you had levels of about 16 ppm germanium and gallium in the lignite, and we were able to, for 1 ton E per day, 2 ton E per day, 3 ton E per day, produce, up to, if we look at both stages of the UND process, for 3 ton E per day, the potential there is to produce about over 20,000 kilograms per year. If you move to, somewhere between 50 to 60 ppm germanium, you move that number to about 70,000 kilograms per year. So that's significant increase. It's also a significant increase in the revenue that a plant like this could the annual growth revenue that could be produced would actually triple from somewhere in the neighborhood of 20, with the 16 ppm, you're looking about 27 million to potentially 3 times that, over 80 million. So that's the potential there for doing sorting and blending, and to be able to optimize the levels in the feedstock that goes to your plant. Also, it can reduce your operational costs as well as waste. The technologies that we look at include X-ray methods. These are some of the methods that can be used in the field. They're basically X-ray fluorescence, field measurements. We also look at prompt gamma neutron activation analysis. These are for belt application. Basically, you have a neutron activation system that's on a belt that can give you the elemental composition. We've been exploring and looking at laser breakdown spectroscopy as well. We also look at several other methods like multi-gamma attenuation. There's new sources out. There's better sources that give you multiple energy levels of attenuation, which can give you both density of the materials and some information on chemical composition. So these devices can, they're smaller. They can be mounted. Here's a DGA right here. These can be mounted on a belt and also on mining equipment. So there's field and belt applications for those. What we've been doing is using neural networks and regression models and other types of models to utilize the signals that you get from these sensors. These sensors they don't have always the ability to actually measure the particular element, but there's other characteristics of the spectra and interrelationships of the different elements to the modes of occurrence and association that we've been able to utilize that information to develop fingerprinting algorithms. So this information has been incorporated and augmented into these different types of methods to improve the measurement of the critical minerals and rare earths. Also, we've been doing feedstock utilizing the prompt gamma neutron activation. We have developed tracking and sorting systems that can go through a handling system, and we have track coal all the way from the delivery point to the burner, and we have sensors, MGA sensors at the burner that validate some of the composition. Also, these are integrated with sorting gates, so you'd be able to sort the coal with higher rare earth elements. In the field, this is an X-ray system. We work with a company that has developed a TrueScan system. This is a system that actually has an X-ray detector here that scans across full cores to give you a chemical composition as a function of location within the core. And this system not only can measure the elements associated with critical minerals and rare earth, but it also gives you the major elemental composition. And the major components like sodium, you should be able to get the ash content, you should be able to do other things. So this could be a significant improvement on the ability to actually do testing at the mine and get some real-time results so you can make decisions on the fly. So what we've been doing here is working with TrueScan and integrating our predictive algorithms into their system. And we've been testing that, and the ultimate goal is to reduce the cost sample analysis, have near real-time results, and they get much more detail for the entire length of the core. You just heard from Ed about some of the stuff is like, changes in abundance in 3 inches, and this will allow you to actually see some of those changes. So this is some of the initial results where we scan across the material. Here's the rare earth element concentration in ppm for sample, or as the TrueScan was scanning across the core. And this is the average composition that we measured with ICP-MS. And here's one where we had concentration at the margin of the scene, and then that dropped down significantly. But this is what we got from ICP-MS. So it shows some possibilities. So what's the status and next steps? We have been working with TrueScan to standardize this for a range of lignites. We've incorporated the predictive algorithms, and the first phase of the field testing will occur in September, and we'll be on site looking at full core analysis. The other part of the whole technology area, the suite of technologies that will need to be incorporated is a method to do tracking, sorting, and potentially blending. We had a Department of Energy project, 4-year project, that looked at the use of PGNAA and multi-gamma attenuation to characterize fuels, actually develop neural networks, and to track the delivered fuel into the plant, distributed, how the fuel was distributed into live storage and silos. And this is used by operators to blend the coal as it goes into the different burners, with respect to fireside performance, and you can do diagnostics if you want. But the main thing is the ability to sort and blend. So a little bit of background here. This is when we incorporated this into the analyzer to determine the rare earth element content. This is the coal delivered to the live storage facility, and this is the base to acid ratio that was calculated. And then we were incorporating the neural network augmentation of the PGNAA and MGA sensors. This is the training data. We would do training of the PGNAA system, and what we do is do numerous analysis on the samples and blends of the samples to be able to train the neural network to be able to make predictions. So this is the training set, and then this is the validation set. You can see that it gets in kind of the mid range of the methods. So that's been incorporated into the algorithms, and this is an example of the potential that we see for being able to track the fuel being delivered to a plant. Here's some spikes associated with the high levels of total rare earth element content in the coal, and this material has the potential to be sorted. So the PGNAA can classify about 20-ton aliquots of coal going through the system. So the status of the neural network augmented PGNAA. We are currently a sub to the UND FEED study to recover and refine rare earth elements from lignite waste materials, and we'll be testing this technology at a plant, and that work begins this month. So that's kind of a snapshot of what we're doing, and we can get to questions later. So thanks for your attention.
Thanks, Steve. Appreciate that. We're going to now turn a little bit of time over to Nolan, who has also done some resource assessment and characterization. And then we'll conclude with John before we open the floor up for questions. And just in preparation for questions, direct your attention to the bottom of the Zoom screen. You do have the Q&A tab that should be available for questions that we can begin getting those queued up and those answers ready for the group. So go ahead and take it away, Nolan.
Thank you very much. Hopefully you can see my screen and hear me.
Yes, we can.
All right. So today I'm Nolan Thaker with the College of Engineering and Mines, not with the ERC, but I work pretty closely with the guys across the street, have for the last number of years. So here I'm going to talk about resource evaluation and then the processing of rare earths and critical minerals in the fast abbreviated version based on the time. So quick check on what the rare earths and critical minerals are. The rare earths are the lanthanide series here at the, let me stick the laser pointer as you can see it. The lanthanide series here at the bottom of the periodic table in scandium and yttrium, usually broken down into the light rare earths of lanthanum through europium and the heavy rare earths, gadolinium through the back of the series, and then scandium and yttrium. And then critical minerals include the rare earths, but also include all these other elements based on the USGS reports. So what does resource evaluation mean? You've heard a lot of geologic evaluation thus far on how rich the resource is in critical minerals, how many there are physically in the rock. What area does this resource cover and what variance over this area exists? And that variance is a very good reason on why sorting is very valuable and trying to average out that variance. Anyone who's worked coal knows that coal in one spot can be extremely different than coal a mile away. And understanding how the rare earths vary in that is important. What impurities is in this resource? Not just the rare earths and the valuables, but what else is in there that you'd have to process and work through. And then also just how much overburden needs to be removed. Is this stuff close to the surface, deep in the pit? Is this something where it'd be right in a current mining sequence so there'd be no new overburden to be removed, and that could be an advantage? Or would you have to change stuff and in essence add a step to remove this? All of those are some geologic concerns, but also there's process concerns in resource evaluation. You can't just pull the rare earth rich lignite and turn it into a magnet with wizardry. There's a lot of technology and processes in between. So what do we need to be able to convert those in-ground resources into those finished goods, the magnets that everyone wants? What environmental concerns and wastes are going to be present from utilizing this resource, typically in those impurities that you have to deal with? And then does this resource have a sufficient economic value with these processes to make a successful business case? Some of the low value rare earths, even if they're in high abundance, may not prove valuable. Some of the very high value heavy rare earths I just mentioned can make this valuable in a very, very lower concentration. So it's that economic case that you're looking for. So how does this apply to critical minerals and lignite? So critical minerals, of which once again rare earths are a branch of, found in a number of different forms and with a lot of different impurities in lignite. However, when we look at rare earths, the majority form we find is in the coal itself in these organic based forms, not in minerals. So you don't have a rock of rare earths in your coal seam that you can just find and pull that rock out. Typically it's bound in the coal itself, which has advantages and disadvantages for sure. These critical minerals, there's a lot of critical minerals in the coal. Some of them are also found in that organic form, partially, but others are found in minerals, such as in pyrites and other rocks. So extracting the critical minerals from these organic binding sites, we found requires far less time. You're not dissolving these rocks, and far less chemical or thermal energy than these minerals. You don't have to heat this up to 300 degrees Celsius under really high concentrated acid to get these things to break down. It's a lot, you can do it a lot faster. So when you evaluate a resource, what you need to know is what critical minerals are bound in which ways, which can kind of inform you on how easy they are to extract, so costs, as well as how much you'll get when you attempt to extract them in that way. So in essence, recovery. And then also what other elements, impurities are bound in a similar way. Those are also going to extract, and then there's going to be impurities you have to deal with. So all of that kind of feeds into just general resource quality. So with all these factors, what are the key decision points that point to a high value resource? Obviously, how much of these critical minerals and which critical minerals there are and in what extractable quantity is a huge impact. If you have lots of rare earths, germanium and gallium, in the thousands of ppm, it's very likely you're going to have a pretty valuable resource. But just because you have lesser amounts, if they're more easily extractable and you get a higher recovery, it might still be profitable. How widespread is this resource? If it covers many square miles, very good chance that's going to be a high quality resource, because then you know that plant that you build to extract it can survive for a long period of years. If it's something you're going to run out of in just a few months, obviously that's going to be problematic to try and pay itself back off. How easy is it to extract and develop this resource? If both physically getting it out of the ground as well as extracting it chemically, if it's relatively easy, then lower purity might work in your favor. If it's very difficult to extract it, then you might have to be more selective in what you need to go with. And then for development, is this a resource that already has permitting, that can readily get permitting and actually be developed and processed? Or is this something that's going to take a lot of money and time to be actually able to use? Obviously that feeds into the quality as well. And then finally, what impurities are going to exist, and are these going to interfere with processing and refining? For lignite, sodium's an impurity for boilers that everyone knows about. But from what we've seen, typically this has almost no impact on our extraction. We get it, but it's not going to interfere with processing and refining, so that's not a problem impurity. There are other impurities that will interfere with those. And so identifying which those are and how we need to minimize how much we get is important. And once again, bringing up the other point is those impurities, you typically have to get rid of them in some way. Are those going to cause environmental challenges, or they're going to be very easy to dispose of and treat? So now getting into the pricing and the distribution of rare earths. These rare earths and critical minerals are not made equal. There's 17 of them. But in terms of the overall product suite of rare earths, there's a lot of different products you can make: glasses and ceramics, catalysts, different end products, and then magnets are the huge one for rare earths. In general, across the whole world, when you extract rare earths, you aim for the magnets, which means, and there's only 4 magnet elements: Nd, Pr, dysprosium, and terbium. And what that means is for the other 13 elements, more often than not, you vastly overproduce how much you need. For instance, cerium, once again, its price is extremely low at $2 a kilogram, $1 a kilogram, which is typically sold actually even at a loss when you refine it. It has a very large market. The market buys 80,000, 90,000 tons of cerium annually. Problem is, to make enough rare earths for the magnets, you end up producing 150,000 tons of cerium. And so you just overwhelm the market in supply. And then obviously the price has to course correct for that. And when you look at these prices, I mean, obviously you've got your magnet rare earths, your light magnet rare earths, neodymium and praseodymium as oxides. In 2020, we're about $50 a kilogram. Now are a little over $100 a kilogram. And those, a lot of light rare earth rich ores exist. So these are typically still a very high price, but a little bit lower than your heavy rare earths, which are far rarer to find. And so your heavy rare earth magnets, your dysprosium and terbium, can range in the $400 to $2,000 per kilogram. Obviously, distributions that include these heavy rare earths and are more enriched in those are going to be far more valuable than your light rare earths. To take an example of the 2 Chinese ores, because they're the only country in the world that produces both light rare earth and heavy rare earth rich ores at the moment. The light rare earth rich ore in China at Bayanobo, which is an iron mine, is about 5% purity. And in essence, it's got so much of the cerium and lanthanum that's pretty much the same price that it's essentially unprofitable if it was any less pure at 5% purity, which for rare earths is actually huge. Whereas if you look at the ion adsorbed clays, which are heavy rare earth rich ore, these are profitable all the way down to 0.03% purity in the ground. So over 100 times less pure and more profitable than the 5% pure, just because they have these other higher value magnet rare earths that most ores don't contain. And then I'd also note for these critical minerals we talked about, and Steve talked about, germanium and gallium, these are on the many hundreds of dollars per kilogram as the purified metal. So when you talk about 70,000 kilograms, you're like, well, that's only 70 tons. Why would I care about 70 tons? Well, at almost $1 million a ton, 70 tons is a pretty big impact. So when we're looking at processing these lignite for critical minerals, once again, our geologic data gives us how much the rare earths are in this lignite. And then what UND's process looks at doing is using that lignite itself, not the coal ash, and then making a few different products. So we make a rare earth mixed concentrate where we pull those rare earths out at a low purity, and then in essence, upgrade them to a high purity and get rid of all the elements that would be hard to refine for the refining process. But we'll actually get rid of impurities and make a value added enriched coal lignite product that you can make carbon products and power out of. Our critical minerals, those germanium, gallium, cobalt, and a few others, would get refined. Once again, the gold is semiconductors for a lot of those high value applications and very needed applications with the recent export controls from China on those two elements specifically. And then the rare earths take some refining, some processing to eventually get it to a number of products, of which, once again, magnets are by and large the target product for everyone. So what UND's been doing in the project, once again, in 2016, we started at about lab scale, 60-gram batches, just how are the rare earths bound in the coal and can we get it out? And yeah, we can. And we got a patent on this extraction technology right away. Then we moved to upgrading and scale to 50-kilogram batches, so about 1,000 times bigger, and say, can we actually make enough rare earths that refiners could tell us, is this, would we be able to refine this? Have you gotten everything out? And what's the first sort of base economics based on this process? And we went through that. And now we're in commissioning a pilot scale where we're doing 10 times that batch every single hour in processing. So a processing week will look at processing between 30 and 50 tons of lignite, to multiple semis at this point. And here what we're trying to do is, does the technology we developed on this bench scale batch process work in a commercially relevant scale at a continuous basis? And do the economics work once we've got everything connected, and how can we make it better? So our next steps for building a domestic industry for these critical minerals, rare earths, obviously we need to improve our knowledge on the characterization, both from the geologic setting as well as making sure that the rare earths and critical minerals in those forms are easily extractable and we can actually process those. Next, we need to design and identify gaps in these first of a kind commercial facilities for extracting these rare earths. Looking at front-end engineering design studies for kind of identifying what we need left to be able to build it. Need to identify and plan our downstream processing steps to making these market accessible critical minerals, not just the small amounts of concentrate and mixed rare earths that consumers can't really buy, but actually the magnets that go into the cell phones that consumers will buy. And then also ensure a robust, stable revenue stream. As you saw in the price curves, in a factor of just 2 years, some of them increased by 300%, some of them got cut in half. The rare earths are a very volatile price structure. And so trying to identify ways to manage that, either through minimum price controls from the federal government that we've pursued, as well as just specific contracts on long-term price agreements, where there would be some stability in terms of a company building these, as well as stable byproducts. If you have byproducts and not all your revenues based on something that moves up and down like crazy, that can obviously inform business decisions pretty well. So that's all I've got for now, and I can turn it back over to Jason and then John.
That sounds great. Thanks. Appreciate you going over that information with us. I've got a couple questions lined up for the bunch of you, but we're going to conclude with John before we move to questions. So John, if you would like to take control of the screen, and you can go ahead and take off with your presentation.
Yeah, thank you. Boy, I've got too many screens to look at now. I can't keep track of what I'm doing, right? All right, here we go. So what I'm going to talk about today is a particular program that we're doing through the Department of Energy, and it kind of encompasses what all your previous speakers have already been talking about. But this kind of takes a step back in more of a general sense. So the Department of Energy recognized that national security is affected by world markets, right? And we've seen that certainly after the start of the conflict between Russia and Ukraine. But there's been other instances where world market fluctuations have greatly affected availability and of components and things in the United States. So they initiated this program to look at carbon ore, rare earth, and critical minerals, and started this initiative that the acronym for is called CORE-CM. And you can see here kind of what their strategy or end goals are, with the big ones being trying to figure out where there are domestic sources of rare earth elements and critical minerals, what it might take to utilize those, but certainly just log where they're located so that they can be utilized in the future. So with that, of course, the Williston Basin is one of 13 initiative programs that were awarded under this DOE program. So we're number 6 up there in case someone's forgotten where the Williston Basin is located. And so we've been moving along with this program, and this just shows you the breadth of support and participation that goes into this program. You can certainly see with our core team here, and involves components of folks from the University of North Dakota, North Dakota State University, the state geologic surveys of Montana, North Dakota, South Dakota, the Critical Minerals Institute. There's quite a few groups that are all branched into this. And along the bottom here are the folks that also have participated in funding for this program. And a company, Current Chemicals, is also helping to provide a little bit of guidance and counsel on certainly as we move along in the future to look at how to distribute this supply chain, like Nolan was talking about. They're going to be able to provide some help there as well. So under this program, the main concept here is just to identify, characterize, and assess. And it's under these 6 basic categories. So we're not specifically focused like Steve Benson and Nolan Thaker and Ed Murphy have been on maybe real specific pieces. We're trying to look at all of that and assess all of it together. So looking at the resources, even looking at things that are considered waste streams. These things we're talking about examples of, like, fly ash instead of just the coal. Produced waters is another example. Looking at those technologies and things that are being developed, like what Nolan was just talking about, assessing those and determining what's out there and available to do this extraction and concentration of those rare earth elements. And then looking at the business side, at least at the high altitude level, and trying to work out what those strategies are for developing the infrastructure, being able to bring in industry. How is that business developed? And then that even goes into, our technology innovation centers needed for things such as training the workforce to be able to work into this field. Also help to draw in the business to be interested in this region. And of course, there's always a component here to do education and outreach. So the main focus, though, is on just characterizing that resource. So taking what Ed and Steve and Nolan are already doing and trying to help expand on that, trying to help identify where the gaps are in the assessments that are being done, within the Williston Basin here. And that goes, like I mentioned, beyond coal, even into ash, produced water, even shales we are seeing do have some potential here to contain possibly extractable rare earth elements. And even to look at things that are a little more novel, like trying to find ways to, in place, do extraction on those resources that perhaps are a little too deep to do surface mining techniques like we typically do here in North Dakota. So this map here just is a section of just showing the data that we've been collecting through the Core CM program. And this data is a collection of data coming from it's coming from Ed Murphy, the folks at main campus through Nolan and Dan Lodahl is also helping to provide info. Other work that's being done with North American Coal in their mines, BNI Coal, other facilities in the state, and also this this database called Coal Quality. There has been work done in that decades ago that does have some useful data on the content of rare earth elements and critical minerals. And so this map just kind of lays all that. This is the North Dakota-Montana border, North Dakota-South Dakota border here. And it kind of shows where a lot of this data is coming in. And if there was a way to quickly overlay, you'll see that a lot of this data is directly overlays what Ed had been showing earlier here in the presentations. These dots don't show individual data points. These dots are just showing locations where there are a multitude of samples being gathered here. And so as we work in this Core CM program throughout this year and into next year, it'll be wrapping up next year. We're also going out now and working with Ed, for example, and trying to help him gain a few more data points in those locations where his data has been suggesting that it looks very promising, and we were getting high total rare earth element counts in the analyses that he's been doing. Excuse me. So these green areas just kind of lay out general locations where we're potentially going to be able to go out and aid and add to what the other folks today that have been presenting add to that data and the overall knowledge that we have for the Williston Basin. Not to rehash too badly, because everyone else has been showing data plots right on concentrations, but generally speaking, if you take all that data from those locations and you start to plot them out, you'll see the ranges there that the other folks have been speaking of. But we're highlighting some that we believe, because of demand and current price structure, seem to be promising. That there's some good potential here. These are for the rare earth elements, and then this here are for just the general critical minerals that might be found within the coal. And there are several here that we find promising even within these. Some of these are, you notice they're high concentration, but they're considered low value. So it's not necessarily that they're being ignored, but what it means is that we're not going out and actively looking for those sites expressly on those concentrations. So with all of this data, what we've concluded, if you look, this is the same chart that Nolan had shown just a little earlier, but now we've outlined in yellow those rare earth elements and those critical minerals that we feel have the greatest potential to contribute to the market that could be developed within the Williston Basin. So those would be the target elements that we would be going after through, the work that UND is doing. And as you see, of course, gallium and germanium are right in there on that list and are points of focus. So if you look at that whole structure then of what's contained in the coal, and then you start to work through this extraction processes, things that Nolan and others at UND are looking at on the extraction side. And you start to split that out. Not only then do you get to do the critical mineral extraction and the rare earth elements, but there are also uses for that material after the extraction has taken place. So you have this depleted lignite where those elements have been removed. That is still able to be used in a facility that produces electricity, coal-fired power generation. Also, there are other things that can be done that go beyond just the critical minerals themselves. Carbon is a critical mineral, and that carbon can also be converted into graphite and graphene and other carbon-related materials. That's also very useful. And so there's potential there. So the idea is thinking about total utilization of that material, that ore, that we're now considering coal. It's not just a fuel, it's also an ore. And so trying to do maximum usability of that material. And all along these points, anywhere, and Nolan has stated this in the past, anywhere that you're producing a solid is an avenue for a business possibility. So this is a simple overview where all of these points, there are multiple potentials for business development in these areas. And so as we look at the Williston Basin now, and we look at what we believe is contained there and what we may be able to extract, then we start to think about, well, is the infrastructure here to make it economic for us to actually get that material out into the nation for use? And certainly we see the Williston Basin as a business hub. Infrastructure wise, if you look at the map down here, this is just showing railway, specifically the BNSF railway system, but we have highway connections all the way through the US, and we even have access to ports, with Duluth being the closest. But looking at rail and highway, it's easy to see that it's not difficult to get materials to ports located in Texas and the ports that are located over in Washington and Oregon State. That actually we feel we're in a pretty good position, and a lot of that infrastructure is already in place. And certainly as we move along here, we feel that probably the greatest potential here to start this off would be at facilities being created near the mine, just like our coal-fired electrical generation is, as a first step. And so all of that is pretty much ready to go and accessible. And so we have the transportation. And of course, if you're going to do it by the mine, you're near power plants, energy is not an issue. And we do have the water availability to be able to carry on this kind of work. And so real quickly here as I wrap up, because I want to make sure we got time for questions. Within this Corsium program, I had mentioned doing the education and outreach. And so we have been doing our own series of webinars. So here's my small shameless plug. We've done 4 already that you see listed here, going from just a general discussion about critical minerals all the way through how are we going to move forward with their utilization, what does business look like, what are the needs. This particular one kind of expands a little bit on what Nolan was previously just talking about here, about how you get from the process all the way to the products. And as we look forward in the future, we do plan to have a couple of more webinars that we're working on that we plan to do in September and November of this year. And also we held a seminar last October in Bismarck, a one-day symposium that we felt was very informative and successful. And we're going to do that again this year. And so if you're interested, be thinking and be looking, here is the link to our website. Feel free to go there anytime. We have our webinars have been recorded. They are there that you can watch and review them. We also have the slides that were presented are on that site. And so be thinking about this. Details will be coming soon about this symposium that we'll have posted on that website you see there. And with that, I'm going to stop so that we can be ready for questions.
Sounds good. Thanks, John. I'm just gonna ask for one slight correction on one of your slides, John, because I get excited about what you're showing. And 2 or 3 slides back, when you're showing all the different elements of opportunities, you got the critical minerals, you got the critical mineral depleted lignite going into the power plant and the carbon byproducts. We've also got the carbon dioxide opportunity, which is yet another one of those value-added opportunities. Theoretically, what I love about that slide that you showed is everything coming out of the ground, including the electrons, can be monetized. And when you stop letting this valuable byproduct of CO2 go into the atmosphere, that's just one more product that can be added to our suite of economic growth that we're doing here in North Dakota. So I love that slide that you put in there. And I know the concept is echoed with a lot of what our other presenters are doing. So thank you to our panelists for the preparation, the slides that you put together. I'm going to begin with a question that I hear all the time, and I'm going to direct it to any one of our panelists that would like to answer. Because what we hear in the industry from time to time, whether it's from policymakers to members of the public, we've been talking about critical minerals for several years now. And I think when all you hear is the highlights of critical minerals every 6 months or whatever, you get the sense that, oh, we've been talking about this for a few years and we're always talking about it. What we've seen is the research and development has really progressed by leaps and bounds. The commercialization kind of needs to come after that research and development happens. So my question to you is, let's assume that the research and development continues as successfully as it does. What are we looking at? What are you all looking for commercial partners? What is it going to take, to say somebody walk in off the door or in the door with $1 billion and says, I like what you've done, help me build a business. What are you going to tell that person needs to happen? And what do you want to see that person be offering you guys, and how to make that happen? So like I said, whoever wants to take a crack at that first, go ahead. And if anybody else would like to follow up, please feel free.
Yep. Well, I can take the first crack at that. So, I mean, in terms of kind of where things are and commercialization wise, that final slide and all those next steps that I mentioned, all of those are underway right now. There's additional research and analysis on exploration for a number of avenues. That FEED study that I said really gets us to right to that pre-commercial basis was just awarded by the DOE, and we expect to start basically any day now on this first of a kind plant. We've got partners looking at those processing, the refining, and making magnets downstream in the U.S. So that's underway. And really, I think this is coming together in very few number of years, honestly, 2 to 5 years, when we're actually going to be able to start springboard this industry. That being said, what we're looking for from industry and kind of what we need moving forward, obviously the resource is good, but also we need really buy-in on who's willing to take some of those first of a kind risks on building this plant, operating this, knowing that revenues are fluctuating in rare earths. I mean, terbium 5 years ago was $500 a kilogram. Now it's over 2,000. Europium 10 years ago was almost $1,000 a kilogram. Now it's 20. And understanding that fluctuation occurs and being able to take those early risks, I think that's really what's needed, and kind of where that burden is moving to industry is evaluating this research and saying, am I willing to do this or not?
I agree with everything that Nolan just said, and I'll also add that along with that, even though we have identified and realized that we have the infrastructure in place to do this, siting for not only these initial extraction facilities, but all the resultant components of that as it goes all the way to market still has to be placed as well. And I will tell you, I was just talking yesterday to Beaver Brinkman, who for the city of Beulah is their economic director. And Beulah has got a really good forward-thinking handle on this, and they're thinking towards the future already. And so they're looking at what would this look like for the city of Beulah? What infrastructure do we need to improve upon? What are the enticements that we need to bring in the workers? And then along with that, well, what is needed to educate those workers so that they can competently be interactive in this new technology-driven industry? And so there's a lot of work going on that, and it's all needed, all of this. And like Nolan said, it's ongoing right now. And Jason, like you had mentioned, it's gained momentum. We say the wheels are in motion. They're spinning now. And so and they're big and they've got momentum. So I don't think it's a matter of anymore that we're trying to get them to spin. They are. We just need to make sure they stay spinning and maybe speed them up a little bit. But we're still looking. It's going to be a few years down the road before we're even breaking ground on significant components of this. And so even though we have the momentum, patience is also of the essence as we try to work through this. There's a lot of challenges here, and the work that Nolan and Steve are doing, it's not simple. If it was simple, we'd already have markets, right? And so there's a lot of hurdles to get through, and but we're getting through them, and we're working around the ones that we can't solve, and it's really taken on control, especially over the last 5 years. It's amazing now how this has become the main topic of conversation in a lot of conversations.
Yeah, good example is what we're doing now with the Germanium and Gallium project. That's funded by the Department of Energy, and we're in phase 1 to develop the conceptual design for a plant that will take it from the either ash materials or the primary feedstock will be the mixed rare earth element concentrate that comes from the UND process. And we have the refining people, we have the people that can take it all the way to the metal and to the pure product that are involved in this phase 1 project right now. And we're right now writing the proposal or the research plan, the teaming plan, and that sort of thing for phase 2, which we anticipate will be happening within the next few months. I expect the solicitation to be coming out. However, because we had this project, I've been interacting with the Army and other groups in the Department of Defense that have expressed some interest in saying, where are you at? What does it take to get this up off the ground? We need X number of kilograms and germanium or gallium for their systems, and they're not going to have a source. So this, I think, germanium and gallium is going to be accelerated. At Microbeam, we've actually been working on germanium since 2004, where we were extracting it from gasification ash, and that goes back many years, but that kind of slowed way down when all the infrastructure moved to China, and so we just put that on the shelf for a while. So I think germanium and gallium is going to come along quite quickly.
So all three of you touched on this in different phrases, but talking about de-risking it is the next phase of commercialization. Yeah. Is it, my understanding, I'm sure is incomplete. I talk about that when I'm talking to policymakers is economic de-risking. We can't have the Chinese undercut the market, for instance. But is that the only de-risking that you guys are interacting with? Is that the major risk, I guess, that needs to happen de-risk and commercialize? What other things are you hearing from potential commercial partners that they're looking for completeness on? Because that's where we think we can be successful. For instance, talking about Beaver, Representative Novak in the past legislative session had a great bill that was going to added tax credits for commercialization facilities that might eventually produce some of these critical minerals. So we're interested in being partners in this as well, and I think the legislature is. So what are the next steps for de-risking where we can be impactful? And Steve, I'm just going to put you on the spot and ask you first, because I know you got a hard stop at 3.
Yeah. The clients that we have that want to buy the germanium and gallium products, is the main thing is you have to have the purity levels, and you have to have the consistency, and you have to have a feedstock that's going to, that is definable. Okay. The feedstock is going to be available, and you'll be able to keep this process running, because we're going to need germanium and gallium. So feedstock reliability as well as purity is key. So they need 5 nines plus. That's 99.999 plus % purity. So
okay.
I'd also say on de-risking, I mean, there are still technical risks. I mean, this is being piloted for the first of a kind now. There's risks on the IP and in essence the downstream refining and metallization and making magnets. And do we have the IP and in the United States, not just this team, but in the United States, and how do we do that? So those risks exist. Obviously, that the financial risk on unknown revenues, since these prices move around, is a significant one. It's one I think the federal government is buying down on, both through some talks of doing a minimum price, but also just from things like in the Inflation Reduction Act, the tax credit on the electric vehicles only applies if the critical minerals are made in the United States, which in essence creates a pseudo market that the US critical minerals could be a higher value than non-US critical minerals, because they will have that tax incentive and non-US ones won't. So there is process in de-risking that financial risk on those first of a kind, but it's something that in essence, I think a lot of it has to come more from federal agencies kind of helping to de-risk that than a company could necessarily do, unless they get really interesting with contracting, for instance.
Yeah, the only piece I'll add, and to even take a little bit step back, we cannot speak enough about just the basic characterization of what's out there. I mean, there are years and years, if we had the luxury, that could be taken just to characterize what the resource is and where it lies, and just the overall volume. I mean, you don't want to start to explore what seems to be a highly economical resource area, then only find that there's 8 months or a year's worth of material there. You don't want to build up a whole system on that. So, characterize. And the other thing on the economic part, if any of you follow DOE funding announcements, you'll notice certainly in the last year, they've really been coming out with many, and they're across the whole spectrum, from the characterization part to the extraction, to doing basic processes specific to magnets, to recycling. There's a lot out there, and all of that with that federal support is helping to de-risk as all of these technologies get developed. There's not a single solution to any of this.
Yeah.
There's going to be multiple technologies there, and that's a way they're being de-risked.
Thanks. I'm going to have kind of a 2-part question. I'm going to start it with Ed. If you others have input, please feel free. Number one, coming from our chat, Lauren asked, who owns these rare earth elements and critical minerals? What is our ownership regime in the state of North Dakota? So question one. Then the second one, which follows John's recent point about characterization. As a state, are we doing enough to give you the tools necessary for that characterization phase where our potential commercial partners have a long-term vision of what the resource looks like over the next 30 years? You know, we've been mining coal for a very long time in North Dakota. We think we have it accurately characterized. Where are we on that timeline for critical minerals and who owns them ultimately?
So, as far as I know, it goes with, when we're talking about in coal, it goes whoever owns the coal minerals. I could be wrong. If, you know, the problem in recent years is that people have been, we've had a couple of calls from people who are looking at conveying or not conveying over minerals, and wanted specifically to hold on to the critical minerals. And if they could write those out separately, and I said, well, you know, we're really not the ones to, that's not our area of expertise. But again, if it's tied in with the coal, I said my first thought is that you couldn't separate those out, but I really don't know that part of it. So my first thought is that it would still stay with the coal if they're found within the coal seams.
Sounds like there may be an opportunity for us to provide some clarity on that issue if there isn't, because to me that would be part of the de-risking process, is making sure that there is no dispute, or at least there's a clear path to monetization for those minerals. So we will have our legal team to take a crack at that too. Second part of the question, characterization. Is the state doing its part? Are we keeping up with what the commercial partners are eventually going to need?
Well, I think, you know, we've kind of spun our wheels for a number of years where we would find these high concentrations throughout the coal-bearing rocks, and quite often, sometimes we'd go back and we would sample 50 feet, 100 feet laterally in several directions. In some cases, the very highest concentration we found was the first one, which was very frustrating. Other times it would go for perhaps a few hundred feet and then go away. And then we figured out why that was happening. And but once we got, in recent years, we got to the Bear Den and the rain bed. Now we're talking about the horizon, which I mentioned before, for both are roughly 30 feet thick. That extends for tens and hundreds of miles. So this has changed very quickly, where now we've really got horizon to target, 2 horizons, and now we just got to find the right thickness of coal that falls within that. And again, these were these paleosols, these ancient soils developed on existing rock. So it's luck of the draw if it developed right and where you got coal in the exact right position.
Okay. So next question, and I know we're starting to wind down here. So let's kind of consider this the final thoughts. And again, we'll start with you, Steve. I've long considered that our competitive advantage in this is the fact that we have fixed cost infrastructure already in place that is in large scale excavation and moving of earth that contains the resource. However, that entails, bringing these industries together and, basically integrating the processing plans with existing mines and power plants. Is that a competitive advantage? Are there disadvantages to co-locating in such an integrated manner? Or should we be looking at breaking off that critical mineral processing capability, extraction, refining, and making sure that it is done in a discrete fashion?
I think taking advantage of existing infrastructure is an advantage. However, I think things will need to be changing. There's going to have to be selective mining. There's going to be a lot of that type of thing. But I think you can you can utilize the mining infrastructure. Also, you can use the coal combustion systems and the gasification processes that can help in the refining of some of these components. Some of them you need hydrogen. So there's really some good opportunities there. However,
so I'm going to jump in. and just interject something too. Does that worry potential investors who they say, I just want to come in and do one thing? And you're making this more complex than it needs to be by talking about this large scale integration, or am I just making stuff up at this point?
Well, these plants, and Nolan can probably talk about this, but they're gonna have to process quite a bit of material. And the infrastructure there to process that material exists. Whether or not the degree of integration, I don't know exactly how that's going to occur. The other piece of it is if you could have a centralized location to do the processing, maybe you could bring in some of these rich rare earth element containing critical mineral material to this central processing plant. So, that's my
That was one of the that's one of the ideas that we've kind of kicked around is, could you incentivize the creation of a centralized processing facility? And I think they did something similar to that in Oklahoma, if I'm not mistaken, where they're building some processing capability down south. But continue that thought, Nolan.
So as a quick aside on the prior question about the exploration, I mean, for a standard mineral project where you're developing a new mine somewhere around the world, it's not uncommon to sink $10-20 million into exploration. So in essence, the sky's the limit almost in exploration and what we can do. We're not going to run out of things to explore and understand. In terms of kind of that integration, I mean, there's a lot of pluses in those integrated systems that Steve is talking about. The complexity, there have been questions on, in essence, how does the contracting work if it's a third entity? How does the permitting work if it isn't a third entity and it's buried in one of the two, either the power plant or the mine? And what does transportation look like? There have been a lot of questions and there not a lot, but there have been some questions and concerns on that and what that will look like, and that's yet to be seen and determined. But I think in general, it's still a major advantage. I mean, if we were to build a new mine, now mind you, we are still looking at some of these really high zones elsewhere that would a new mine that transports to a centralized facility work here? Obviously, that's of consideration, but building these new mines would be extreme costs and delays in getting this up and running. The US needs it now, and having this fixed infrastructure would both incentivize and speed up that process to getting this to market, rather than having to go through a lengthy permitting process on get the mine and then do everything behind it.
I'll just throw out there real quick, again, agreeing with both what Nolan and Steve said. And certainly for us here in North Dakota and the Williston Basin area, I think the true major advantage to get any of this going and to entice business to come in is the fact that we have a united, concentrated effort at the research level, at the state level, even at the county and city level in some areas in the state, where everyone wants to see this concept succeed. If you look at locations certainly east of the Mississippi River, they don't have that type of integrated effort. There are a lot of hurdles for a multitude of reasons, but we're pretty unified here, and we all want to see this move forward. And that's it seems to me that's a huge plus for anyone wanting to come in, because there's full support from the capital on down to try and help you be successful in developing your business in this area.
And let me just, we had one more question come in, and I think it'll be a pretty quick one to answer. I think, Nolan, it was you talked about UND holding a patent. Is this on what the process that you've developed to extract that rare earth element material from lignite? I guess I could surmise that there's probably quite a bit of IP that you've also developed, Steve, over the years. But particularly, is that UND's IP that you were referring to, Nolan?
Yeah, to extract it. We've got 2 other patents working through their process now, and in a sense, filling out the rest of our processing train to get some IP protection. not all of our secret sauce is in those patents. We do hold things because once you patent something, anywhere around the world can read it. I'm certain Steve has a number of patents he's working through on both the sorting side as well as some of the germanium gallium fronts, but also just some trade secrets because of the sensitivity of putting all this out publicly. And mercifully, DOE has also been very cognizant of sharing all of these public data would be a very significant negative in a lot of cases. China has Lignite too. Russia has Lignite. If we show them exactly how to get it out, we can be shooting ourselves in the foot really fast on a national scale.
Yeah. Well, that takes us to our 3 o'clock endpoint. Thank you to our panelists and participants for the work that you put into this, for sharing your time with us. Again, thanks, John. You mentioned the critical mineral webinars that you've posted as well. I've participated in a few of those and would recommend them as well. So thank you to our panelists and participants, and stay tuned for more of these webinars as we continue to develop this suite of coal-related issues. So take care, everyone. Thank you.